Hello everyone, so I'm going to teach you chapter 19 and 20 today. The topics are going to be linear patterns and curve patterns. And what do we mean by curve patterns? We mean patterns that they don't look like a linear relation or a line, and they're not representing a line. So we need to differentiate the two linear and nonlinear or curve patterns. And make sure every time we want to analyze these type of problems, if they are not looking like a straight line, we use a curve model or a curve equation to analyze them. Alright, so in chapter 19, there is an example, and that example is about what's the relationship between the price and the weight of diamonds. So this question is about price or cost of diamonds. So we are selling diamonds, and there's a price to it, right? How can we estimate or know the price or cost of a diamond with a certain amount of weight? That's the actual question. If you think align data, so consider two questions about these diamonds. What's the average price of a diamond that weighs 0.4 carats, and how much more do diamonds that weigh 0.5 carats cost, right? So to answer that question, let's say one of these is given and the other one is not given, or both of them are not given. How can we actually come up with a price for these two diamonds with this amount of carats, right? So what we do, we normally use past data. And using the past data, we come up with a scatter plot and then come up with a regression line. You learned in the previous sections on chapter 6 that we can use correlation to find the association strength, and after that we can find a regression line equation of the regression line or regression model to find values that we don't have. So you can see here, using a sample of diamonds of various weights, regression analysis produces an equation that relates weights to price. So where are these numbers coming from? These are historical. These are past states that we had. A certain amount of diamond with a certain price at different times are provided, right? So let y denote the response or dependent variable, price or cost, and let x denote the explanatory or predictor variable or weight. So that's a scatter plot we come up with. It seems pretty much linear, it looks like a line, and the variations are not that much different. We calculate the correlation R, and correlation R is 0.71. 0.71 is between 0.6 to 0.8, so you can consider this as a strong relation. P-value is below 0.05. As a result, we can say that this is a significant correlation, right? And we can say this is linear association. Equation of a line. So this is the equation of regression line that we fit, and it identifies the line fit to the data by an intercept. We show it with B0, intercept, we show it with B0 or beta 0, and a slope b1 or beta 1. The equation of the line is y hat equals to the intercept plus the slope b1 times x. X is your independent variable or the explanatory variable. And these two equations are actually exactly the same thing. We're just writing the interpretation here. So on the left hand side, what do we have? We have estimated cost. On the right hand side, we have weight. So weight is the actual weight of a diamond, but so weight is actual weight of a diamond, but the cost or the price is not. The cost or price is actually an estimation of the price. And why is that? It's because we are using these different values, different from past values, to create that regression line. So when you create that regression line, each of these points are are not exactly on the line. They are far from the line. They have a distance from the line. Distance from the line, distance of each point from the line, is considered as an error. So that error, or we call it in statistics, we call it residual. If the point is below the line, that's a negative error. It's on the top of the line, that's a positive error. So the sum of these errors, these errors actually create the total error, right? So whenever error is involved, so whenever we don't have exact values, that's an estimation. So estimation is, in fact, we're approximately calculating the value for that diamond, or calculating the cost or the price of that diamond. And what we can see here is always, for this semester, remember, we always consider the response variable or dependent variable as estimated. So y hat is estimated, and it's coming from intercept plus the slope times explanatory or independent variable. And going down here is the residual, or errors are explained here. What is the residual? The difference between the estimated value for response, y hat is the response, y is the actual value of the diamond, or actual cost of the diamond. So the difference between these two is the total error we calculated, and we show it with the E for error, and we call it residual or errors. So the best fitting line collectively makes the square of residuals as small as possible. So there are many lines can go through the data and fit to that data, but only one of them has the minimum distance from those points. There's only one line that has the minimum distance from those points, and that line is called regression line. The choice of B0 and B1 minimizes the sum of the square of the residuals. And this is, let's select two of the points, one on the top of the line, one below the line, right? These are the past data. So you can see the distance, the difference between the point, the height of the point, and the height of that line. And same here. If the point is on top of the line, that's a positive error, negative error, right? What do we call them again? We call them residuals, right? So they can be positive or negative. Top of the line, positive, below the line, negative. Okay, fitting a line to data. So what formula do we use? Remember that we don't use these formulas on my exams, but to answer questions on homework and the final exam, you might need to remember and know these formulas. So the B1, which was your slope, is calculated by correlation R. So what is R? R is the correlation that you learned in the past, times SY. What is SY? What S represents standard deviation of Y, and Y represents dependent variable or response variable. So standard deviation of response values is SY. You multiply it by correlation and divide it by standard deviation of x values or explanatory values or factor. How do we calculate the B null, B0, or the intercept? We calculate it by bar. The Y bar is, bar means average, mean, average of response values times B1. So B1 we already calculated in the first part. We substitute it here, times average of independent variables, values, or explanatory values. So if we do those calculations for the diamond example, so this is an example in the book and you can read it. Read it for the details. So the least square regression equation came up as this formula. What's the formula? Y hat, or estimated cost or estimated price, is equal to 15 plus 2,697 times the weight. And how do we interpret that? So we can see, before interpreting, there was a question. The question was, what's the approximate or average estimation of a diamond's price for a diamond that weighs 0.4 carats, right? So that's 0.4 is replaced by weight multiplied by 2,697 and add 15 to it. Estimated price comes up at $1,093.08. For 0.5, you just substitute 0.5. You substitute 0.5, you will get a number 270 higher than 1,093. So the difference between the two, right, 0.4 carats and 0.5 carats is just approximately $270. I think it was, I calculated myself, it was 269 something, so we rounded up to 270. And that's the scatter plot that we explained. That's a fit line going through the data. You saw the equation, and this is for 0.4, 0.5 for weight. What's the price? It's right there. Okay, so interpreting the fitted lines, or interpreting the intercept. So the intercept is the portion of y that is present for all values of x. So intercept, in fact, is not dependent on the value of explanatory variable or independent variables. No matter what the independent variable is, the intercept is always the same for your response variable. So normally if you put x, or you put the IV, or weight in this case, 0, whatever is left is your intercept. And how do we interpret it? It really depends on the topic. In this case, because it's about the price or cost, so it can be considered as a fixed cost. So fixed cost, when you're selling diamonds or selling any products, there are always fixed costs there, right? So normally we can say our intercept is the fixed cost for this type of question. But let's say you have a question that the response variable is not really cost or revenue or price, but it's, for example, something like percentage of body fat. The question is about percentage of body fat, and your intercept, let's say your intercept is negative, a negative value. How do we interpret it? There is no interpretation for it, because negative value for percentage, especially percentage of body fat, there's no negative, there's no meaning for it. It doesn't make sense. So for those type of problems, you do not answer. You do not have to answer. You can say there's no interpretation for that intercept. Okay. So on your homeworks in the future, from chapter 21 to 26, you're going to have questions that the intercept doesn't make sense, and one of your multiple choices will be it doesn't make sense, or there is no interpretation. Remember, you check if it doesn't make sense, you check there is no interpretation on the answers. Okay. The intercept estimates the average response when x is 0, where the line crosses the y-axis. So that's perfect. Okay, so the next part will be interpreting the fitted line, interpreting the slope, right? So the slope estimates the marginal cost used to find the variable cost. Marginal cost is 2,697 per carat. That means every carat of weight increase in diamond, right? There's $2,697 added to the value or the price of that diamond. And again, this is in average. This is estimation. This is not exact. So why is it not exact? And there is a range of around this 2,697. It's because this calculation is coming from averages. In addition to that, do all diamonds have the same quality? So they have, with a certain weight, they have exactly the same value? The answer is no. So there are other actually variables involved, right? And also we have another example here. So this example is in the book, so I want you to read this. So we are pretty much done with the chapter 19. So let me move to chapter 20. But before going to chapter 20, I want you to open the file companies with no outlier on JMP. Open companies, no outlier on JMP. Open, go to Canvas and on Files, Data folder, and open the company's data with no outliers. Right, that's the dates. And what we're going to do, I'm going to show you how to recognize if a data set has a linear pattern or it does not have a linear pattern. We can actually do that by comparing a few scatter plots together and see that some of them, they don't look perfectly linear, some of them do look linear. So for those that they look linear, we normally use linear methods. For those that they don't, we use nonlinear or curve methods. So let's go to Analyze to find this to run this comparison. Go to Analyze and go to Multivariate Methods. Analyze multivariate methods and multivariate. So click on Analyze, click on Multivariate Methods and Multivariate. Very simple, right? So click on Multivariate, and what I'm about to do, I'm actually going to create I'm looking for a scatterplot matrix. So what we want to do here, we want to select all these continuous or numerical variables: sales, profit, number of employee, profit per employee, assets, and person profit per sale. What we are about to create is called a scatterplot matrix. Scatterplot matrix. So we're going to see all relations between 2 by 2 of these variables on a matrix of scatterplots, right? So you just select those that are numerical or in blue color, blue triangles on the left, drag them into Y columns. So there is no X or Y, it's just Y columns, and click OK. And what you see here is going to be a scatterplot matrix. So right there. And you want to make this, if you have enough space on your screen, you can make this a little bigger, and you can actually make it as big as you want to see all of them clearly if you have space on your screen. So 2 by 2, you can check, for example, this scatter plot right here in that cell represents the correlation or scatter plot of sales and profit. This is for sales and profit. This is also for sales and profit. So you can see that they are the same, right? But they're just opposite. This is profit to sales, sales to profit. And this one, for example, right here, this one right here is for profit per employee and asset. That's the scatter plot or correlation between profit per employee and asset. And what else does this give us? Other than the scatter plots, we also have up here, if you see these numbers are correlations. So what do we call this matrix? This is a matrix, right? This matrix is correlation matrix, Pearson correlation matrix. Okay. You can see that, for example, bring this down. For example, correlation between number of employees and sales is 0.7. This is strong correlation. Correlation between number of employees and profit is 0.35, which is a weak relation, right? And let's find another one here, for example. between profit and profit per employee is 0.58, which is a moderate relation or association. This one also, asset and profit 0.44, that's a moderate association or relation. Okay, all right. So what I'm going to show you here is comparing linear relations to curve relations. So you can see that, you see this scatter plot right here in the column 1, 2, 3, 4, 5, column 5, row 3. Column 5, row 3 is association between number of employees to assets. Do you see it looks like a line? Looks like a straight line, right? But let's see another one. So for that one, we can use the methods that we used earlier from chapter 5 and what you learned in chapter 19 to create a regression line, and that would perfectly work. But there are correlations that they don't look perfectly like a line, like this one. Do you see this one? Between asset and profit per employee, you see that it looks like a curve, right? And the other example could be, for example, let's go down here, this one right here, association between profit and person profit per sales. So it looks like a curve. It's not like a straight line, it looks like a curve. So we're going to analyze this and see which one works better, a straight regression line or simple regression model or a curve model. So to do that, where do we go from here? So let me bring this down, and I'm going to find a fit line, one time for a linear relation, one time for a curve relation. So go to analyze fit y by x, because I'm doing a one-on-one relation or association. So I'm going to take, for example, I said profit to person profit per sale. Profit to person profit per sale. Profit is your response, DV variable. Person profit per sales is explanatory variable. You just need to click OK. And that's your scatter plot. You want a fit line, click on the red triangle, fit line. That's your fit line. What's obvious here is that that fit line has a problem. Why? First of all, in some part of this relation, you can see that majority of points are below the line, nothing on the top, because the data, the line has to go through the data. It did not, right? In some part they're all below, in some part they're all on the top. That shows a problem in this analysis. That is your equation. That's your R square, 0.49. What does R square represent? If you remember from your past topics, especially if you had it on exam 1, what does that mean? That means approximately 49%, less than 50%, right? Approximately 49% of variation in profit is explained by percent profit per sale. We hope that we can see a R square higher than 50% at least. So let's see if I change the fit as a linear to a curve, because to me this looks like a curve. So let's run a curve analysis. So go here again. We go on the fit y by x again, and we do a profit again, and same thing, right? Percent profit per sale here, and click OK. The same thing for what we did in the past. We have exactly the same thing, scatter plot, but this time we don't want a fit line. We want a nonlinear. Nonlinear, there are many examples of nonlinears. One of them is polynomials. I hope you remember from algebra in the past that, of course, linear is a degree 1 of polynomial, but we can have higher degrees. We can have quadratic, cubic. You can see it here, quadratic. It's a second degree, or power 2, power 3 or cubic, power 4 or quartic, right? You can have power 5 and power 6. If you have too much variation, too much up and down, you can use a higher level of polynomials. all of these are considered nonlinear because they don't look like a line. If you remember from algebra, quadratic, they look like a U, right? Look like a U, so they can expand or they can be narrowed down, depends on the data that we have. So let's use a quadratic first. I used a quadratic. That's you can see that is a curve now as a minimum point, and that looks closer and going better through the data. Do you see that? Here, some part they are below and top, but here there's still a problem of variation, but this is creating a better model, a bit more accurate model. So what can we compare here? We can compare the R-squares. So here, profit is explained by 65%, right? So 62.5%. 62.5% of profit is explained by profit per sales, percent profit per sales. But in the first model, only 49%. How much increase do we have? Maybe about 12.5% increase in defining your variation of your DV. That means more control over DV when making decision using the percent profit per sales, and that's a good thing. All right, so that's not everything we can do. There are a lot more we can do, but the thing is, what we want to do, we want to make sure that when we compare these, we want to make sure that we have a better calculation. So let's do another analysis here, and that would be, let's do go to fit y by x and do the same analysis. Profit, percent profit per sales. Click OK, and this time we're going to use a cubic. So go, click on rectangle, polynomial. We did a quadratic just now. Let's do a cubic, which create a different curve, and compare. The R-square did not change. The degree of formula from 2, it has increased to 3. That means more complexity on calculations, but R-square hasn't changed much. And if you look down here, the p-values of the model, they are not significant. They don't show significant, but in quadratic and in the linear fit, they both are actually significant. And okay, so do I want more complexity while I have the same R-square? The answer is no, I don't want. So I don't want this. I don't want this because it's not that accurate. This is giving me a better model, better calculation, and better accuracy, right? So, okay, now after that example, we have we'll talk about the topic of curve patterns on chapter 20. We'll be really quick on this, and you need to read it from the book. You need to read this from the book, okay? Detecting nonlinear patterns. So what improvement in mileage should a manufacturer expect from reducing weight of a car? So looking at the scatter plot of this problem, which the problem is on the book, you can see that this scatter plot shows a curve relation. How do we recognize that? On one part of the linear regression, most of the points are only on top of the line, and there's just 1 or maybe 2 points below, right? In the other part, also same. Majority of data are below, small amount are on top. So they should be equally on both sides of the line. Points are supposed to be approximately, in average, equally distributed around the line, not majority of them on one side, majority on the other side. Does that make sense? So this is a sign of a problem with the model, because this model is not actually representing our association or relation here. So we create a model. What this plot does is considered or called a residual plot. So what are residuals? Residuals are distance from the regression line. So we put a 0 distance. That line shows 0 distance from the regression line. And each point is showing on the scatter plot how far those points are from. Are they on the top, they're positive, below, they're negative, right? So you can see that they're not distributed everywhere. They're not randomly distributed. They have a pattern. They go down and then they go up. They go down and then they go up. So residuals are going down and up. They should have no pattern, meaning that they should spread almost everywhere, equally on top and bottom of the line. It looks like maybe a circle or maybe like a rectangle. The points should be like a rectangle around the line, but they're not. Okay, so transformation. So this is what we said. If a linear linear equation does not really represent, we can use different types of nonlinear formulas. What are those? We can choose among what you learn. Actually, you learned these in the past. So we can use quadratic formulas, cubic or degree 4 formulas, right? You can use log. You remember logarithm, right? Log function. Or reciprocal function, which is the inverse of log function. And log function, they look like this. Right? They were looking like increasing and increasing to the right hand side. What else do we have? Something that is not explained here or in the book, which is exponential functions or transformations. You remember exponential functions are the one that you have a constant value like a to power x, or e to power x. Exponential functions can be also used for transformation. So, and you learn how to do it, right? So read the book on this topic, and this is the example from the book. And that green line is the curved line that's going actually through the data, and in all of its path going through data has some points on the top and below that line. And this is a better fit. We're not saying it's the perfect, the best one, but this can be a better fit compared to the straight line that the red color, you can see it here. So that's our visual comparison. Okay, so again, we can use many different models, but for your class, we don't really spend on this because we don't want to go through the calculation of the log function. We don't want to talk much about the nonlinear functions. This semester, we just focus on linear patterns and linear equations, which are much more simple. But I want you to know these just because, and especially know how to use it on JMP, because if you become a manager or become a data analyst somewhere in a company, and you can really see that past data of your company, they don't look like a line, but they're analyzing using a linear pattern, you can jump up and say, hey, this is not accurate, don't make a decision based on this. It's better to use a non-linear pattern rather than a linear pattern, and you can create a better model. So you can tell them that. Another option that we have on JMP, I can show you if you open your company's data really quick. The graph. If you click on graph and click on the graph builder. So this graph builder is actually very useful and very advanced. I will just tell you how it works in a very simple format, but you actually need to practice with it and learn a lot from it. Okay, so I want you to work with this, practice with graph builder, and do a lot of things and learn a lot of things. So let's do so this is your x-axis for explanatory independent variable. This is y-axis. This is for your response variable or dependent variable. So let's say profit. I put profit here, right? Profit here. I want to put, for example, percent profit per sales that we did the practice earlier down here. So as soon as you do this, JMP itself, the graph builder itself, actually creates a nonlinear model that has the highest accuracy. of calculation here. You can see that. And from there you can actually get more information. So I want you to work on this. So and click everywhere, try everything, all the summaries, and get all the calculations out. And on the top you can change it to linear if you want. You can see that it's not that perfect, right? You can also create, see if it's a linear relation, which ones are the outliers. So row 15, so I just bring my cursor on top of the point that is outside that area. That's row 26. So these two seems to be outliers. What else can I do? With the 90, this is 90%, so I can change it to 95 or 99% if you want.